Size Statistics video series. My name is Sean Rose, and you are watching the Continuous Outcomes route. This is Module 1, in which we're covering t-tests. And this is video 2, where we're actually going to start walking through an example with a Jupyter notebook and doing some coding in R. And let's see if I can actually advance the slide there. There we go. Okay, so in terms of the tentative series organization, hopefully you are coming from the first video in Route 1 in which we covered a little bit of theory about t-tests. So we talked about what t-tests are, how the student's t-distribution arises. We talked about effect sizes. We talked about how to power a t-test. And today we are going to go through and show how to do a lot of those things using an example Jupyter notebook. And I am going to post a link to that notebook so you can download it and follow along, and it just kicks me out of my slideshow. Anyway, we don't need the slideshow anymore, so who cares? Thank you, PowerPoint, for being a royal pain. Okay, so this is the Jupyter notebook that I'm going to post a link to, and the first thing you're going to see if you're not really terribly familiar with R, which to be honest I wasn't before I started making this video series, I kind of learned it for this series. You have to load a bunch of packages off the bat, things that you want to actually deal with. So tidyverse is actually a collection of like 8 packages. Effect size is going to be useful towards the end of this notebook. Plotly is for doing some interactive plots, and then I'm setting some options to make it so that the plots that get displayed don't take up massive amounts of screen space. I've also got Talk To enabled, the Jupyter Notebook extension, just so you can hop around the document. It's kind of nice. Today I am actually just going to cover the 2-sample t-test. I don't think I'm going to cover the 1-sample t-test at all because it's so similar. In a separate video, I'm going to go into violating and testing assumptions. I also might talk about constructing an f-test that's equivalent to a t-test. The reformatting data section is just in case, for those who are interested in how to essentially do pivoting of tables in R. So yeah, this notebook is pretty long, but I'm not actually going to go through all of it in these videos because I think it would take too long. So today let's just start with the 2-sample t-test. So the first thing we're going to do is we're going to generate a data set that kind of mimics one of the data sets we talked about in the theory video that precedes this one. So let's generate a chunky cat data set. And all I'm doing here, I've got 3 different data sets that you can create if you just uncomment some code. Setting a seed, setting the number of measurements we're going to make, and then I'm generating some example data where I'm pulling from a normal distribution. That's what the rnorm function does. It generates a normally distributed random variable. I'm generating 250 of them with a mean of 16, standard deviation of 4. I'm then actually throwing in an outlier as well because I want to show how you can, by visualization, very quickly identify suspicious data points. Then I'm generating a another population of normally distributed random variables, again 250 of them, this time with a mean 16.8 and a still standard deviation of 4, so same standard deviation as before. Also adding an outlier to that group, and then I'm labeling them as 2 different cat breeds, so this is really mimicking that chunky cat data set I used for the 2-sample t-test in the theory video. So yeah, that's what that does. I'm also throwing in an index just so we can identify data points easily. So you run that, and then run the head command, and I'm running it with the data frame that we created, which is called example. Oh, another note about R for those who aren't familiar. Periods in R, if you're familiar with other languages where periods actually mean something, in R, periods don't mean anything. They can actually just be used in the names of functions or in the names of variables. So you can basically don't put any emphasis on periods in R code. Anyway, to display the data frame we've created, we're going to display the top 10 rows using the head command. It takes a data frame, also takes the number of rows you want to display. If you look at the first 10 rows, this is the index. They're all cat breed 0. This is their weight, or the weights that we're pretending we measured, which are really just normally distributed random variable samples. We could also look at the last 10 rows. So these are all cat breed 1. This is their indices and the weights again. Let's change that back. We can get some summary statistics using some functions from the dplyr package. So we can take the example data frame. We can then create a group by data frame where we group the measurements by the cat breed. And all that really does is it makes it so that when you it creates what's called a grouped data frame, which when you pass a grouped data frame to the summarize function, it performs all the operations that you tell it to group-wise, as opposed to doing it just on the entire data set. So when I run the summarize function here, which you can also do it with a Z, by the way, they use two different spellings, I'm telling it to make a column called count, which is just going to take the number of measurements in each group, make a column called sample mean, where I take the mean of the weight column, again by group, and then a sample standard deviation column where I do the same thing just with standard deviations. And then I'm going to spit out the summary table as I did here, and I've got the two different cat breeds, number of measurements for each cat breed, sample mean, sample standard deviation. These are all the typical summary statistics I might need. Okay, so now let's look at plotting the data, because that is something that you really need to do with any data set that you get. So if I want to plot this data set, there's a number of different ways I can visually represent it. One of the most common ways is to use a histogram. I'm going to use ggplot for a lot of the plots in this. I'm also going to show you how to use Plotly. I'm not going to go too much into the detail of how this code works, but I highly suggest you read up on ggplot. There's a bunch of examples on like the R Cookbook website, and also you can just kind of get a feel from it from this example code. But basically here I'm passing ggplot a data set and an aesthetic, and the aesthetic or the mapping is going to tell it what to put on the x-axis. I didn't tell it what to put on the y-axis here. I'm telling it to color by cat breed and also fill by cat breed. Then I'm telling it make a histogram layer or a geom histogram and do a bin width of 2 and then make it a little bit see-through. That's what alpha 0.5 does. Then I'm plotting some vertical lines at the sample means for the two different population or the two different samples. So run that, just plots it. And as you can see, I get the histograms like I expect. I also have my little outliers hanging out at like 44, and there's another one that's around 0. I think I actually have 2 data points around 0. Yeah, one for both breeds. So one of those is not the outlier I generated. One of those was actually naturally generated by just sampling a normal random variable. I can also, instead of plotting 2 histograms, the other easy way to visualize data for 2-sample t-test would be box plots. So ggplot can, of course, also be used to make box plots. Instead of doing a histogram layer, you just add a box plot layer. So again here, I'm passing in ggplot my data frame example. I'm also passing it a mapping or an aesthetic, where I'm telling it make the x-axis the cat breed, y-axis the weight. Then add a box plot layer. Tell it to make the points that it identifies as outliers naturally, make them a different shape, because I'm also going to use geom jitter to plot all of the raw data points on top of it, and I want the ones that it plots as a part of the box plot to look different than the jitter points. And this is what that looks like. So I get all of these black dots because of the jitter. So if I just knocked that out, I would just get this plot. These points it's identifying as outliers are points that are farther than, I believe, I got to think about that. If you look up geom box plot, it'll tell you in the documentation. I'm pretty sure it's they're points that are farther than 1.5 times the inner quartile range away from the nearest quartile. So if you look at the 75th percentile, 1.5 times the inner quartile range from that should be the end of this whisker, and then all points outside that it plots as quote-unquote outliers. Same thing on the bottom end. Anyway, I've had them plot as triangles so that when I add all of the raw data on top of it as little dots, that you can tell which is which. As you can see, the outlier appears twice in the plot because it shows it once as part of the box plot and once as part of the jitter layer. Anyway, that's one way to quickly plot data. Another way I like to do things is using Plotly, and the reason for that is, and the syntax for it is a bit different than with ggplot, although you can actually, there's a command to convert ggplots to Plotly. But the advantage of doing it with Plotly itself is you can tell it how to be interactive. But the advantage of Plotly is really that it generates interactive plots. And there's other packages that do this as well. I'm just personally familiar with Plotly. But if you look at this plot we made here, we essentially just made the exact same box plot, except we offset the points to the left a little bit using this point pose parameter that we can pass. The really cool thing about this plot is that I've told it to make it so that when you hover over it, it tells you the breed of that data point, the weight of that data point, and also the index of the data point. So this makes it really easy when you're doing a t-test to look for suspicious data points, like, for instance, this guy is way outside, and notice also that Plotly is smart enough to do the whole 1.5 times the inner quartile range thing to limit the whisker size. So you can look for some of your points that are like crazy far outside of the whiskers, and you say, I should further investigate that point. Same thing on this end. I've got a data point that's way down here, which is the one I manually added. It's way outside, 1.5 times the interquartile range from the nearest quartile, so that's something I should really look at. Okay, the last plot I'm going to show is something that in t-tests, to be completely honest, is probably not as important, but it's still something that's good to look at, and that is a QQ plot, or a quantile plot, comparing our samples to a normal distribution. So this is a way of checking if the samples that you've measured are approximately normally distributed. And I'm not going to go into the details of what a quantile plot really is. I'm just going to kind of emphasize, from a visual perspective, if your data is normally distributed, these points should approximately fall along a straight line. And all Plotly is doing here in generating this line is looking at the, I believe it's looking at the 25th and the 75th percentile and just drawing a straight line through it. And it did that for both cat breed 0 and cat breed 1 because I told it to do what's called a facet wrap, and to wrap by cat breed. So it makes multiple different facets or multiple different plots by cat breed. Anyway, because our data actually came from a normal distribution, obviously it is normally distributed, but this is just an idea of what QQ plots can look like when you even have normally distributed data. A lot of people early on when they're doing statistics look at plots like this and they look at the tails and they're like, ooh, my data is not normally distributed because I got this little bit of a deviation from a straight line towards the end. That is completely normal to see in a real data set. Even if you have perfectly normally distributed data or data coming from a normal distribution like we did here, you're gonna see funky stuff like this, particularly if you have smaller sample sizes. So I encourage you to go back up to the top, play around with setting num equal to like 10 and stuff and see how the QQ plots look, because deviations from normality look different than having this little funkiness towards the tails of the distribution. So anyway, those are the kinds of things you can plot and ways to quickly identify outliers. Now let's actually run a t-test and get an effect size, some of the things that we talked about in that theory video. So running a t-test in R is like crazy simple. I mean, we're talking one line of code. So I'm setting the variable t.result equal to function t.test. I pass it a formula. You can read this as run a t-test on weight by cat breed, and then pass it the actual data frame in which the data is stored, and in this case our data is stored in this example data frame. So this runs the t-test. This actually runs a Welch's t-test. If you want to run a regular t-test, so not accounting for unequal variances between the populations, you can set a flag var.equal to true. That will do a classic student's t-test as opposed to a Welch's t-test. And then I'm going to print out the result. I'm also going to calculate Cohen's d, that's one of the effect sizes we talked about, and I'll calculate Hedges g on top of it, which includes a correction to make it less biased for small sample sizes. Again, you basically do the exact same thing. You pass it the formula weight by cat breed, and then set data to be equal to example to tell it what data frame to look at. Hedges g you get just by actually using the exact same function. You just pass it a parameter called correction and set that parameter equal to true, then you're going to get Hedges g. So anyway, let's run that, look at the results. The result of the t-test, it gives you this really nice, well-formatted thing. It tells you it's a Welch's two-sample t-test, tells you your data was weight by cat breed, gives you the t-statistic, the degrees of freedom determined by the Welch-Satterthwaite equation, tells you the p-value, which in our case is 0.15, so it's not significant at the 0.05 level. It explicitly states the alternative hypothesis, which is kind of nice because I didn't actually manually set it here. You can manually set it. But you see it's a two-sided hypothesis test here because we say the alternative is that the true difference in means is not equal to 0, so it's not less than or greater than, it's just not equal to. It also spits out a 95% confidence interval, which we talked about how it calculates that in the theory video, but it gives you a 95% confidence interval on the difference in means. So the difference in means, it thinks with 95% confidence, lies between negative 1.27 and 0.2-ish. It also gives you the sample estimates of the means in group 0 and group 1. And then these outputs, these two little data frames, are just the outputs of Cohen's d. So this is our estimate of Cohen's d. It's about negative 0.13. That means our two sample means are different by approximately 0.13 of a sample standard deviation. It also gives you a 95% confidence interval on Cohen's d, which is nice. Hedges G, actually in this case, because we have a pretty large sample size, Hedges G and Cohen's D are almost identical, so it pretty much spits out the same thing when you set correction equal to true. Again, I encourage you to play around with generating this data with like less data points and seeing that Hedges G and Cohen's D can actually differ. So then, here we've seen that we had outliers between our two groups. So we looked at cat breed 0 and we have an outlier on the high end, but then the median of our cat weights are actually lower than for group 1. But in group 1, we have an outlier on the low end. So that's actually interesting because we have outliers on opposing ends, and that's sort of opposing the effect we might want to see, which is possibly that cat breed 1 is a little bit heavier on average than cat breed 0. But when I ran this t-test here, I didn't actually see a statistically significant effect, and my Cohen's d actually includes 0 in the 95% confidence interval, which is consistent with the fact that I didn't see an effect at a 5% level. So how can I address this? Well, one thing you can do is you can go and remove the outliers, and this is something that, when we're playing around with canned examples, we just kind of do willy-nilly. But in practice, obviously, you don't remove an outlier unless you've actually looked at, well, why is this data an outlier? So if this was like a measurement of a patient's like water equivalent diameter off of a CT scan I got from PACS, and it was way higher than average WEDs that I saw from other patients, I would go back to PACS, I would look and see, how did our measurement get messed up here? Is this a real outlier? Was this just a really big or a really tiny patient? Or is this an outlier where I had my code that calculated WED just messed up because I wrote it poorly or something? Anyway, here we're going to very quickly show how you can identify these outliers and remove them. Obviously, you can identify them just from the box plot in this really contrived example. So I can look at this one, I say, oh, the index is 251. So I can remove that one by that. I can look at this guy, index is 502, going to be really easy to remove him as well. So to remove those outliers, I'm going to make a new data frame called example without, and I'm going to take that data frame and run the dplyr function filter. And this pipe command, by the way, just passes this argument as the first argument to the next function. So it takes example without, pass it as the first argument to filter, and then remove the rows that have indexes equal to 251 and 502. Basically tell it, select all of the rows for which index is not equal to 251 and index is not equal to 502, which is those two outlying data points. Then I'm going to rerun the t-test and print out the results. Also going to get a new Cohen's d. Then I'm going to print out the old t-test for comparison. So let's look at those results. So I've checked the number of observations first, just using the glimpse function, and I forget honestly what package that comes from. But anyway, it's just telling me how many observations are left, making sure I removed 2 data points like I was supposed to. Here is the output of the 2-sample t-test. Again, shows me all of this nice stuff. I get a t-statistic, and here, note, my p-value is now 0.0434, meaning if I'm looking at the 5% level to determine significance, I now have a statistically significant result. I can reject the null hypothesis at the 5% level, and that is consistent with the 95% confidence interval I get for Cohen's d here, which does not include 0 in the 95% confidence interval. Note the old t-test, my p-value was 0.15, and my Cohen's d did include 0. Note, though, that if we were just looking at effect sizes, it's actually not that huge of a change just removing those 2 outliers. So my point estimate of an effect size went from negative 0.18 to negative 0.12. So, the sample means are separated by either closer to 2/10 of a standard deviation or closer to 1/10 of a sample standard deviation. So, it's not as huge of a difference as it might sound, and that's one of the other reasons I really like. I talked about reasons I like effect sizes in the theory video, but that's one of the other reasons it's really nice to look at effect sizes is, p-values you kind of interpret with this almost binary interpretation of it's below 5% so it's significant, or it's above 5% so it's not. When really, that's not how these things are. They lie on a spectrum, and this change from a p-value of 0.04 to 0.15 may seem like a big deal because of the whole reject the null hypothesis thing, but in actuality, the change to the effect size is really not that big. Ignoring those outliers and just running the t-test with them in the data doesn't really change the result that terribly much. Okay, so we've talked now about how to run a t-test, which, as we talked about in the theory video, running a t-test is all about controlling the rate of type 1 errors, or the rate of, or the probability of getting a false positive, falsely rejecting a true null hypothesis. But what about if we want to talk about powering a t-test? So looking at constraining the probability of a type 2 error, i.e. rejecting a, or I'm sorry, accepting a null hypothesis when in fact the null hypothesis is not true. So let's assume that we have an effect size, a Cohen's d effect size of 0.8 over 4, meaning that the means are separated by 0.8 and the standard deviation is 4. And this is actually the exact parameters I used to generate the chunky cat data at the beginning. So that's 0.2. And let's calculate the power of a two-sample t-test as a function of the number of measurements given this effect size. So what I do here is I set the effect size. I'm going to set the delta, which is the difference in means, to be 0.8, standard deviation to be 4. I'm going to look at number of measurements, all integer number of measurements between 100 and 500. And then I'm going to do the power analysis, which is really simple in R. It's just power.t.test. I pass it the number, and I also pass it the delta, which I'm actually passing it Cohen's d as the delta here. By default, the standard deviation parameter of this function is 1. So if you just pass it Cohen's d as delta, that will give you the correct power result. You could also, and I show it in the commented out code here, you could also pass it delta and pass it the standard deviation. Either way works. As I show in the theory video, the non-central t-distribution it looks at really only depends on the ratio of delta and standard deviation. So you don't have to pass it both. You can just pass it the ratio. Anyway, all of that nuance aside, I'm then going to generate a data frame with the results, and I'm going to plot it with ggplot. So this is the power of the test as a function of the number of measurements for a two-sample t-test in which we expect an effect size of 0.8 over 4 or an effect size of 0.2. And what you would usually do with this kind of a power analysis is you'd look at this curve and say, okay, when does it cross whatever my desired power level is? And a lot of times sort of an arbitrary one that people pick is like 0.8. So I say, okay, I have a power of about 0.8 at about, oh, I don't know, 390 something. So I need about 400 measurements to get about 80% power with this experiment if I have an effect size of 0.2. And that's how you power a t-test. The one-sample t-test, I said I wasn't going to go over it, but just very, very briefly because I'm already doing all this anyway. This is generating a paired t-test data set, and paired and one sample to me are the exact same thing. Some people kind of separate them, but they really are mathematically the same thing. Anyway, it's the exact same as the data that I talked about in the theory video. I've got cat weights measured in 2019 and 2020. They're paired. I can get summary statistics real quick using the dplyr functions in the same way I did in the two sample. I can plot the data in the same way as I did in the two sample. Here I'm histogramming the differences in weights between 2019 and 2020. And you can see here I've generated data where apparently the sample mean is pretty much 0, so this is not going to be a terribly interesting data set. And does that make sense? Yeah, and if you look at this code here, the first 250 measurements has mean 16. The second 250 measurements has mean 16. I could change that to make this a little bit more interesting, and that's probably the one I'll post. Doing this again. Now the sample mean is actually a little bit above 0, so there we go. Again, you can do a box plot like we did before. We can check normality like we did before, do all of this stuff. But the main point I want to get to is running the actual t-test. So if I want to run a t-test with the data in this format where I've got two columns of weight in 2019, weight in 2020, instead of reformatting your data and doing something fancy like that, you can actually just pass t.test, the function, those two columns. So this is just the weights in 2019, the weights in 2020, and then pass it the option paired equals true, and that runs the paired or the one sample t-test. You can also do the exact same argument, it turns out, to the Cohen's d function, so you don't have to reformat your data before running the test, and that's really just the kicker I wanted to get to. With that, I'm going to end this video. In the next video, we'll dive into sections 4, and maybe, if I'm excited about it, section 6. We're going to talk about what happens when you violate some of the assumptions of the t-test, like violate the assumption that you have normally distributed random variables and such, because turns out t-test is really, really robust, which is one of the reasons that it has the popularity it does. And I really hope that this section convinces you that you don't need to jump to a non-parametric test necessarily, because it turns out the t-test does a pretty good job even when things aren't normally distributed. Anyway, thanks for watching the video. It's been a lot of fun making it, and I hope you have a good rest of your day.